we want to use power series to find ODE solutions, especially for variable coefficients. Yeah. But before, we did one simple example. Yeah. Before we use it to do more examples, we need to, prepare a little bit. So here the main preparation is about convergence. Convergence. Yeah. So we need to make sure our power series is convergent. Then we can apply operations on it. Yeah. All right. Because in order to study the convergence, we define partial sums, Sn. Definition, the first n plus 1 terms of the power series adding together. So we define that power sum. Partial sum. Yeah. That partial sum is always defined, because you never need to worry about convergence. Finite number of terms. Yeah. So no convergence issue. Yeah. Yeah. Then, with that sequence defined, then we consider the limit of this S sequence, partial sum sequence, limit, based on the calculus, the definition of limit of the sequence. Yeah. So we can consider that. We can calculate the limit of the sequence. Yeah. Here, assume the limit exists. If the limit exists, here we use the notation S function. Little s function, because before this point, we didn't define that little s function, right? Yeah. There is no s function. But after we assume the limit exists, then we define s function right here. Yeah. How do we define s function? The s of x1 value equals the limit of Sn of x1. Yeah. Yeah. If the limit exists, then the function value is well defined. Yeah. So that's the way we define this S function, the limit function. So it's a limit function. Okay? All right. Yeah. So then with this notation, then we can go back to the original power series. Here, power series. Now, what is the value of the power series at x1 value? The same as the S of x1. The same of the limit of partial sum sequence at x1. Yeah. So that's the, theoretical background. Yeah. So here we get a, arrangement, setup. This is setup. Still not the, the critical property yet. Yeah. So we will get that critical property related to the convergence. Look at the title, convergence interval of power series. We need to get that. How to determine convergence interval of power series. Yeah. All right. Yeah. Now, continue. Next, we have a formula to calculate the convergence interval. There is a concept called the radius of convergence. Radius of convergence. Okay? Yeah. All right. So there are two formulas both equivalent. You can treat as two versions, both equivalent. You can derive one from the other. Okay? Both equivalent. Yeah. Sometimes the A version is more convenient. Sometimes B version is more convenient. Okay? Yeah. You just choose one. That's easier for you to calculate the radius of, capital R, radius of the convergence. Yeah. The meaning, the meaning is also simple. Yeah. x0, you treat it as a center. x0 is the center. Okay? Then, with x0 as the center, you draw a circle, the radius. Okay? Circle. With capital R as the radius. Yeah. Then, all the point inside that circle, the distance to x0 center less than that capital R, the value is convergent. That's simple. Value is convergent. Okay? Yeah. Even including complex case. Yeah, because when you draw a circle, all the points inside the circle could be complex numbers. Yeah. Even for complex numbers, you plug into the power series, it's convergent. Okay? Yeah. But remember, for our class, when we apply power series, we only assume real numbers. In our power series, we do not consider complex numbers. Yeah. So that's why, although it's a circle, but we only consider interval, convergence interval on the line. Yeah. The intersection of that circle with the x-axis line. Yeah. Line. So it's a interval. Okay? Yeah. Yeah. But just let you know, yeah, if we, if we consider complex numbers, yeah, it's also convergent. Yeah. All right. Yeah. Okay. Yeah. So these two formulas. Yeah. Next, let me show you a few simple examples. We can apply these two formulas to calculate the radius. The first one, e function. Yeah. Expansion of e to the x, the e function. Yeah. We can do Taylor expansion, yeah, or also some people call Maclaurin series, yeah, expansion. Yeah. All right. Using the b version here, using the b version, so then we calculate the limit. Yeah. The limit, because the denominator, so here, denominator goes to infinity, yeah, and so the absolute value, that number goes to 0, and the b version, we take a reciprocal. Reciprocal of 0, that's infinity. Okay? So here it tells us, if you use the power series of e function, then every point, every real number, it is convergent. Yeah. You don't worry. So there is no divergent case. That's so good, right? Yeah, every point, so see, this sequence, every x, you plug in the sequence, all convergent. That's the best we can get, right? Yeah. Yeah, but for other power series, we may not have this great property. Okay. All right, look at second one. 1 over 1 minus x. Remember the geometric series. Geometric series, all coefficients of the power terms, all 1. Yeah. So then by the b version, radius r equals 1. Equals 1. All right? So only when x, absolute value of x, less than 1, it's convergent. Otherwise, it's not convergent. Okay? Otherwise, it's not convergent. Yeah. One special case when x equals 1, it's not convergent, divergent. Yeah. So this case, you need to be very careful. Okay? So the convergence interval, you always need to be aware of the convergence interval when you use this power series. Yeah. The second example. Third example, another special one. This time, the coefficients of the power terms, all right, yeah, and yeah, so here n factorial, n factorial over m, yeah. So n plus 1 goes to infinity. 1 over infinity, r equals 0. That means no point is convergent, right? Yeah, no point is, yeah, other than the center 0, yeah. No point on the plane is if you plug in, you get a convergent value. No. Yeah. So this is the worst case. Here you can see with these three examples, the top one, the best case. Yeah. Everywhere convergent. The bottom one, the worst case. Everywhere divergent. Yeah. The one in the middle, you know, ordinary case. Yeah. So you have a certain convergence interval. Yeah. With that interval, many of our theorems, you know, we can apply many nice theorems to solve ODE problems. Yeah. So for the middle one, if we have the property like this, it's good enough to solve ODEs. Yeah. We do not require as strong property as that one. Right? Yeah, that's too strong. Yeah. We do not need that strong. Okay? All right. Yeah. Oh, yeah. Julie. Yeah. All right. Yeah. So we just finished the first slide. Yeah. Okay. Yeah. Next one. Yeah. Existence of power series solutions. Yeah. So next. Yeah. So here we do some theoretical preparation. So we want to see if we take this approach, is it possible we can find a solution for the ODE? Yeah. So here, yeah, a theorem will guarantee that. Yeah. So let's study this theorem. Yeah. Our target, this second order ODE with variable coefficients. Variable coefficients. Okay? Yeah. 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 And we know for the general case, we cannot solve using our knowledge from the previous semesters. So we have to, so this chapter 5, yeah, we will learn we need to use the new method to solve it. Yeah. All right. Yeah. So that the theorem. Oh, before we look at theorem, we need to learn this concept, analytic function concept. Yeah. Let me explain what is called analytic function. Yeah. Here we require these three functions, PQR, analytic functions. Yeah. So let me give you the definition first. A function f of x is called analytic at a point x equals x0. Yeah. Because we want to do the power series expansions for this f function with the center at this point, x0 point, with the power series expansion. Okay? Yeah. So now, this analytic function should have the following strong property. Yeah. What's the property? If it can be represented by a power series in power of x minus x0 with positive radius of convergence. Yeah. You need to use the concept, previous slide, radius of convergence. Yeah. 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 Within that circle, radius, yeah. center at x0, then you draw a circle, capital R. Yeah. We calculate that the radius. There is a formula we calculate. Okay. So within that radius, that circle convergence, yeah. All right, so, yeah. So this f function can be represented with positive radius. Yeah, here. We emphasize positive radius because in the previous slide, our third example, we have a 0 radius, right? That cannot be used. 0 radius. Yeah. So we exclude that 0 radius case. Must be strictly positive number radius. Then we can define analytic function. Yeah. All right. So with positive radius of convergence, now we can have this theory, existence of power series solution, this theorem. Yeah. The theorem, equation 12. Yeah. So you see this one. The equation 12, if P, Q are three functions of x functions are analytic at x equals x0. Analytic. Okay? Yeah. So we do power series expansion or Taylor expansion, yeah, because you get a power series approximation. You can treat it as approximation. Okay? All right. Yeah. Yeah. Solution. Yeah. Then every solution of 12 is analytic at this point and can thus be represented by a power series in powers of x minus x0 with radius of convergence r positive. Yeah, that's the theorem, simple theorem. Yeah, yeah, pretty straightforward. Yeah, yeah, three coefficients. Yeah, and we can expand them as power series at the same point x0, yeah, and with positive radius of convergence. Here we can assume they have three positive radius of convergence, R1, R2, R3, yeah, because the radius may not be the same. Yeah. Capital R1, capital R2, and capital R3. Yeah. Let's assume R1, the radius of convergence for P function. Okay. R2, radius convergence of Q function. Okay. R3, radius of convergence for R function. Yeah. Then, when we apply this theorem, yeah, because when we consider the convergence point x, that point should fall into all three circles, right? All three intervals. All three intervals, yeah. So we define this capital R, radius of convergence, capital equals the minimum of R1, R2, R3. Minimum. Yeah. So then, when you apply this theorem, we know we can find the power series solution for this equation, and that solution has the radius of convergence, capital R, equals minimum of those two radius, positive radius. Okay? Yeah? Yeah. All right. So this theorem, it guarantees if the condition, given condition is satisfied, coefficient PQR satisfied, we can always find the power series solution. Yeah, that's great. Yeah, although the computation could be hard, but we can apply computer software, right? Yeah, so we can use software, Yeah, but after we understand this method well, yeah, definitely you need to practice hand calculating. Yeah, but so if for your everyday work, so definitely you can apply computer software tools, yeah, or write programs even, yeah, to find the solutions. Yeah. All right. Operations on power series. Then, after that theorem, convergence, solution, existence of, yeah, so now we know it's there, yeah, but we need to find that solution. Our next step, we need to find the formula. Yeah, we need to calculate the coefficients of the power series of the solution. Yeah, but to do the calculation, we need to apply operations on power series. Yeah, here, this slide, yeah, we will have 4 operations. 4, yeah, these 4 pretty much enough to help us find the power series solutions. Yeah. Yeah. We already use them. Here, just we can treat as a summary. Yeah. We already use them in our first simple example. Yeah. Yeah. Our solution y function takes that power series form. Yeah. And we need to calculate the coefficient, A coefficients. Yeah. Yeah. All real numbers here. Yeah. No complex numbers, all real numbers. All right. Yeah. Yeah, but here, when we look at the operations, we consider the two generic power series. Yeah. Just two arbitrary power series. Yeah. Yeah. All right? Yeah. Then we apply, we do certain operations on these two power series. Yeah. All right. With radius of convergence capital R positive. Yeah. Yeah. All right. Then let's do operation, the first one. Yeah. Yeah. 1, 2, 3. The first operation called a term-wise differentiation. You take derivative. Take derivative of the y function. Yeah. Y prime equals, then you take summation on the term. Each term is just a derivative of the general term of the original power series. Yeah. Yeah. Why it's correct, right? So, because people may ask, how do you know this is convergent, right? In this convergence interval. Yeah. There is theorem to prove that. Yeah. So here we just use it. Yeah. 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 So in the power series theory, yeah. Yeah. So here we cannot talk about the whole theory. Yeah. So there is a proof for that. Yeah. So we do not worry about that. Yeah. All right. Yeah. So you can do derivative in this way. Yeah. Yeah. In the convergence of the interval. This is the convergence interval. Yeah. All right. Yeah. Number 2, second operation, term-wise addition. When you want to add two power series, you can do term-wise addition. Yeah. All right. Here, adding these two power series, you just do term-wise the coefficients. Yeah. Yeah. Add them up. Yeah. For the result power series. Straightforward. Yeah. That's legal. Yeah. When you do operation like this, it's legal, it is correct. Yeah. All right. Number 3, term-wise multiplication. Yeah. This one a little harder. Yeah. Think about, you do multiplication of these two power series. Yeah. Computation, very complicated. Yeah. All right, so here's the formula. Yeah. All right, so multiplication. Yeah. All right. Then the product, another power series, the coefficient is given in like this. See? The coefficient. Yeah? A, M, B0, you can see the sum, the subscript. Sum of the subscripts, A0 plus M equals the degree number M, term degree number M. Each term, you have that property. Okay? So not too bad. Not too bad. Yeah, but you need to add up these M plus 1 products to get a new coefficient of this term. Yeah. That's the product. Okay? Yeah. 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 A little hard, yeah, but yeah. Sometimes we may need to use that formula. Okay? Yeah. All right, number 3. Yeah. Number 4, vanishing of all coefficients. Yeah, we also use this property before, vanishing. Yeah. When you have a power series that equals 0. Think about it. When you have a power series, the whole power series, if you know this whole power series equals 0, okay? Yeah, for every x equals 0 everywhere, okay? Then you can derive all these coefficients a and for all coefficients equal 0. We already used this property, okay? Yeah. So these 4 properties should be enough for us to solve ODE using the power series. Okay? Yeah? Yeah. Yeah. All right. Only the third one is a little hard. Yeah, we didn't use third one. Yeah. When we solve, we use number 1, 2, and 4. We didn't use number 3. Yeah. Yeah. It's rare to use number 3. Yeah. It's rare. Yeah. So, yeah. Yeah. But, so there is, small chance we may use the third property. Yeah. All right. Yeah. Yeah. So next, special Legendre equation. Here, let us work on this example. Yeah. Yeah. Special Legendre equation. Yeah. Let us solve this equation. Okay. Yeah. Second order, linear, homogeneous, ODE, yeah, homogeneous, but the coefficients, variable coefficients. Yeah. And if we do not use the power series method, consider older method, we may not be able to solve it, right? Yeah. If we can only use our older knowledge, we may not be able to solve it. Okay, yeah. So here, yeah, let us try the power series. Yeah. It occurs in models exhibiting physical symmetry. Yeah. So in physics, yeah. So the background, yeah. So this equation derived, so in physics, yeah. And it's a important equation in physics. Yeah. Physical symmetry, spherical symmetry. Yeah. All right, solution. Power series form, yeah. And we may use the summation form. Yeah. 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 All right, then 2, yeah, just multiply 2, term-wise multiplication, yeah, and the derivative. Derivative, all right, yeah. And then you multiply variable coefficient minus 2x variable coefficient minus 2x, yeah. So you get that summation. Okay, yeah, all right. Double prime, this summation. M start from 2, okay, yeah, because from 0 and 1, all 0, yeah, so starting from 2, yeah, all right. Then you multiply 1 minus x squared, yeah, yeah, here we can actually, remember last time I show you we use m prime represent m minus 2, so we can change to this summation. Yeah, we can change the m. Yeah, but m start from 0. Yeah, because m minus 2. If this is the new m, when m equals 2, it start from 0. Yeah, so that expression. So when you do calculation like this, you should be very careful. Everywhere. Yeah. Yeah, it is not easy. Here, I do not know what kind of questions I can assign you. Yeah, because usually computation relatively complicated. Yeah. All right. Then you multiply minus x squared. Yeah. When you minus x squared, you should use this version, because x squared, you plus minus 2 plus 2, then it's gone. Okay. So when you calculate this term, you should use the first summation expression, not the second one. Okay? The second one, when you use this 1 multiply y double prime, you use the second one. See? Yeah. Yeah. All right. Because we try to make the general term, we'll try to control the general term as the a sub m times x to the m. Yeah. Yeah. This general term, minus 2, because we cannot do addition directly, right? Yeah, we have to make them the same general term, then we can do addition. Okay? All right. Yeah, but here, minus 2, when we multiply x squared, minus 2 is gone. So we get the same general term, xm times x to the am times x to the m. All right, general term. All right, yeah. All right, so I list, do preparation. Yeah. Then, yeah. So here, for the first few terms, yeah, y prime. Yeah. Second, then we align. The same power term, we align vertically. Yeah. Yeah. So then we add them up. Okay. Add them up. Okay. All right. So that each power term, then use the property for vanishing property, right? All coefficients vanishing. Yeah, that property. Yeah, we get these equations. Yeah, yeah. All right. Yeah. So here, if you work, for example, these two numbers adding together should be 0. Okay. Yeah. A2 plus A0, then you get this one. Okay. All right. Here, minus 2A1 plus 2A1 cancel out. 6A3 should be 0, so 3 should be 0, so on. Okay? Yeah. So you get all these equations. All these equations. Yeah. All right. Then, yeah, here you can see when you write the final solution. Yeah, here you can see all these equations. Yeah, other than A1. Yeah. So here we do not see A1. A1 is a free constant, right? It can change. It does not rely on A0. Okay. All other coefficients, all other A coefficients rely on A0. Okay. A0. Yeah. A0. Yeah. Yeah. So then you have two parts in your solution. The first one, A1 times X. A1, original A1, it's still there. So you can change A1 free, any A1 value, yeah, you get a solution. Yeah, change A1 free. And A0, you can factor it out. Then inside the parenthesis, you have one explicit power series. Yeah. That's the solution. That's the general solution with two parameters. Two parameters. Yeah. Look at the new method and the solution. The only difference, if we compare with our old examples, only difference is one of the solution is a power series. Yeah. Yeah. If this power series is convergent, then we're fine, right? Yeah. Convergent, then we are fine. Okay. Can you see? So from the coefficients, can you see what's the radius of this convergence? Radius. If we have the formula A version, B version. This time, A version is better. Yeah, B version also okay. Yeah, A version, B version. Yeah, both version, fine. Can you see the radius easily? Yeah. Take mth root. A version you take, take limit mth root. Okay. Yeah. Mth root definitely goes to 1, right? When m is very large. And B version, yeah, B version, there is something, yeah. Oh, then you may worry about the B version because we only have the even power terms, right? Even terms. Odd term coefficient 0, if you do division by 0, then you cannot take a ratio, right? Yeah. Yeah, yes. Here, use this chance, I point out something. Yeah. So those two formulas, two version formulas, yeah. Those two versions are limited. Yeah. So for this case, yeah. This case, if you apply directly, you cannot. Okay? Yeah. But if you treat x squared as one variable, then you can apply, right? X squared as one variable, yeah. But there is another version, yeah, another more general version, yeah, yeah. So sometime later, let me bring that more general version, yeah. Then the general version you can apply on all power series, yeah, yeah. Even you have zeros, many zero terms. All different cases. Yeah, because here, there is a possibility. If you look at those two versions, there is a question. How about the limit does not exist? It's possible. Yeah. Limits. When you calculate using those two formulas, the limit may not exist. That could happen. Yeah. But when we use a new, more general version, we know the limit always exists. Okay? Yeah. So for any power series coefficient, the sequence, we know the limit always exists. Yeah. So that can be proved. Yeah. Yeah. So sometime, later, sometime, let me show you those two formulas. Also very simple, but you need to have a new concept about the limit. Yeah. All right. So so we're here. That is the part A. Yeah. So we finished part A. Yeah.
So what exactly is the general equation? What would be the answer to this question?
General, not equation. So here so let me go back to.
We're solving for y, aren't we? Like solving for y for this equation?
Yeah, solving for y.
Yeah.
So
like down there, what would be the
this is the general solution.
So we would write that.
Yeah, you write it. That's the final version. Yeah, final version. Yeah, because for this one, don't worry about this one. Infinitely many terms, because we use computers to do the calculation. Yeah. Yeah. So in the real application, we use numerical. When we need to calculate the values, we use numerical values. Yeah. So don't worry. Yeah. So with computers, so we have a good solution. All right. So you treat. So this is a good solid solution. Yeah. Only thing is in the convergence interval. Okay. You can only do operations in the convergence interval. That's the only limitation or restriction. Yeah. Yeah. Not everywhere. not everywhere. Yeah. Here the radius is 1. Okay, if you get outside 1, then you cannot. Okay, the radius is 1. Must be strictly inside. So the absolute value of x must be strictly less than 1. Then you can calculate your solution. Equals 1, even equals 1 you cannot. Okay, x equals 1, the second part, 1, 1/3 minus 1/5 minus 1/7, and so on. Divergent. Yeah. So you can see that, right? Yeah. So sum of reciprocals 1 over consecutive integers, that's the natural log of n, approximately. Natural log. Natural log, goes to infinity, so divergent. Yeah. All right, so that's part A. Yeah. So we finished part A right here. Yeah. Let me move to part B. Yeah. Yeah, so let me quit quit and show. Yeah. And show. Okay, all right. Oh, sorry, 3 people outside the room. Yeah, I just see. All right. You can go back to, sorry, 3 people. Yeah. 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 All right. Part B. Yeah. So although we are very close to the break time, but so let me just get started. Yeah. So we will. Yeah. All right. Part B, Legendre's equation and polynomial solutions. B.1, Legendre's equation. We just solved a special case. Yeah, the previous example, Legendre's, but here the general, more general differential equation. Yeah, solve this time. So you can see the only difference is here, n times n plus 1 times y. Yeah. In our previous example, n equals 1. 1 times 2, 2y, right? Yeah. Here, yeah. So that's from the physics problems. Yeah. So one of the most important ODEs in physics. Yeah. It arises in numerous problems, particularly in boundary value problems for spheres. A little background for this equation. Yeah. So, all right. Power series. All right. Solution. Apply the power series method. Yeah. Now, because after we prepare ourselves, convergence, existence of the solutions, those 4 operations, now we feel comfortable. Yeah, we can use power series to solve this ODE. Yeah, the standard way. Y power series, Y prime, and Y double prime. Yeah. So we put there. Then we need to do operations. Yeah. First, so here you can see we plug in into the original equation. Yeah. 1 minus x squared, we need to multiply y double prime power series. Okay, and one thing this K, we use K to represent that n times n plus 1. Yeah. Yeah. Because it's a constant number. Yeah. Constant number. So we use a K to shorter expression, K, to represent it. Yeah. All right. Next, it is a little hard to see, but a little hard to see, but we need to be patient. The first one we split into the first two terms. 1 times the power series, x squared times that power series. All right. So the second one, all right. The third one, all right. But this 2 minus 2, can we change to the same general term? By changing the, m value. M starting from 0. All right. But here, so when we change, we use this new variable s equals m minus 2. New s variable equals m minus 2. Okay? Yeah. All right. So, it is a little complicated. If you want to verify, you should be very careful. Okay? So here, I do not do the verification. So here, like that. Later, when you get home, we can calculate carefully. Okay? All right. Continue. Compare first two terms. First two terms. That's easy, relatively easy. Vanishing property number 4. First two terms, the coefficients should vanish. That's the two vanishing coefficients. All right. The general term is this expression, and it should vanish, so we can find a recurrence relation like that. Recurrence relation. Okay? All right. So then we need to do analysis here. After we derive the recurrence relation. Because look at the structure. S plus 2. Recurrence, the two coefficient numbers relation, the difference subscript is 2. That structure tells us some special property. Okay? Tells us some special property. All right. Let me pause here so you take a break. When you come back, so when you have fresh mind, so then we continue. Because this part, a little hard to understand.